Thank you so much for coming to our talks this afternoon. It's a pleasure to be here. I almost have to apologize. I'm going to be talking about time periods of 50 or 100 years, maybe 150 years amongst geologists, So I'm just spitting in the ocean compared to the time frames you all generally deal with. Got it? Okay. I did change one word in the title, climate change claims meet the scientific method. And this just means people like me, and there are only a few of us left in the world, build real data sets to check the claims that people make about the climate. So we'll go through some of those today to let you know what is going on with that. The first slide is just an introduction to the whole idea. It looks a little complicated. I might have 4 or 5 kind of complicated slides. All I want you to see is that this is the atmosphere that is in that blue box. The surface of the Earth is the green line at the bottom, and those numbers tell you the amounts of energy that are exchanged between the two and from the sun that comes in. What you see here are numbers, 24, 6, 100. Those are big numbers. We are talking about, in terms of the carbon dioxide impact, half of one of those units. Now, when you look at that system over time, you find those numbers change by multiple units, from 24 to 27 evaporation, or 100 to 105 up and down radiation. So we're talking about a tiny part of some very large variations. And to try to tease out a signal of what that 0.5 of a unit does in the energy budget is a pretty tough thing to do. So the first claim I want to talk about is claims about surface temperatures, and these are the temperatures you measure from little weather stations, whether you're in the Arctic on the left, or as is one of the most popular ones is the Phoenix site, which is in a parking lot at the university, so you can imagine what kind of temperatures that thing's going to show. But what those surface temperatures, when you sort of average them around the world, you get the bottom chart there that shows for the last 30, 40 years a pretty steep, or at least a rise in temperature. But that really hasn't engendered a lot of excitement on the world as a whole, because when you look at the left chart, if you're able to see it well enough, you find out you're talking about tenths of degree. And so it's hard to get people excited about temperatures changing by tenths of degrees. So our good folks, many in the federal government, try to figure out a way to make an exciting picture. And so this is an image of year-by-year ratios. If you see a blue bar, that means there were more record cold temperatures than hot temperatures, the ratio. If you see a red bar, more record high temperatures than low temperatures. And you see as you go toward the end there in the 2000s and so on, the last 20 years, my goodness, there's all kinds of record high temperatures being set and hardly any record low temperatures. 7 times more high temperatures in 2012. Well, I know how to build those data sets, and so I went in to look at exactly what's going on here. We have a numerator, high temperatures, a denominator, low temperatures for those red bars. And so I was able to basically reproduce their chart with the best stations, except I went back to 1895 instead of 1930. But I do get there at the end, the last 20 years, these very high numbers, and they're red. More high temperature set than low temperature records in the United States. Well, let's look at the years in which the record high temperatures occurred in the United States, and that's what you see. The occurrence of record high temperatures is not increasing at all. In fact, if you draw a trend line on that, it's actually decreasing. The 10 highest years in which record high temperatures were created in those 804 stations occurred before 1955. Record high temperatures are not increasing at all. The story is in the low temperatures, and you see here that as you go the last 30 years or so, a very dramatic decline in cold weather temperatures. And when you put a number on a denominator and make it small, you're going to blow up the number that you started with. Well, the reason for that is interesting, because on the left you see how we take the nighttime temperature. It turns out the nighttime temperature is in a boundary layer that gets cold at night. The upper air really doesn't change much temperature, but you have warm air above, cold air beneath, and that's where that minimum temperature is taken each day for a cold record. Now on the right, you see what happens in the daytime generally, is that the sun heats up the ground, there's convection, and so the maximum temperature in the daytime is really a reflection of a deep layer of atmosphere. It really tells you what's going on with the deep layer of the atmosphere. By the way, that's where the greenhouse signal is strongest. Now, that's the pristine condition I'm showing there, but what has happened over time, if you look at the right side, you see that when you build buildings, you change the roughness parameters for wind, and so you create turbulence that brings in the warm air down. It can't create the cold air layer that you see on the left. When you put aerosols in the atmosphere, they also block infrared radiation, keeping it warmer at the surface. So over time, as we have developed the surface with buildings, orchards, farms, aerosol-emitting places, we have created warmer nights. If you go to the San Joaquin Valley of California, where I'm a native, if you look carefully, you'll see this green axis there in the San Joaquin Valley. That's supposed to be a desert. That should be light tan in a natural setting. But because we have changed an entire valley with irrigated agriculture, it's now dark green. That changes the energy budget. The cities there, when I was born in Fresno County, there were 50,000 people. Today, there's 1 million. So that city has really grown like crazy. Here's the temperature for that city in Fresno. Since 1888, the high temperatures show essentially no change, actually slight downward trend. The nighttime temperatures, though, show a large warming trend, and that is an indication that you have built up your infrastructure around the weather station so that you can hardly get cold nights anymore because it's mixing down that warm air from above. And so my view is that the official U.S. government chart you see there is deceptive and misleading. It's due entirely to nights becoming warmer, not days becoming hotter, yet that is the notion you are led to believe when you read this government report. In fact, when you look at heat waves, you see there that heat waves were much more frequent and stronger in years past. Another thing, rainfall and extreme rainfall events are going to increase, and so you see pictures like this, most put out again by our federal folks, that show these upward trends of heavy rainfall events like downpours and so on like that. But when you look at them, they kind of start in years that are odd. Why start in 1958 or why start in 1950? We've got plenty of records to look at for rainfall. So I went back and I dug through actually data that went all the way back to the U.S. Signal Corps and Fort's recorded rainfall. And so using 10 stations in the southeast, one of them was Shreveport, by the way, and 10 stations on the Pacific coast, I built a data set back to 1860s and so on. And here you see the downpours. And downpours have not increased in frequency or really in amount either. So when you go back far enough, you have a big enough data set. And again, I apologize, we only have 150 years or so against geologists who like lots of zeros after their years to find out what's going on. But I hope you see what we're doing here. We're checking all these claims with real data and expanding the data set so that we can find out what's really going on and avoid that cherry picking that we see often in this debate. Here's another one. If you think about every 5 years, find the heaviest rainfall event that occurs. So this map tells you that if it's green or blue, there's been a real big increase in these heavy events of rainfall. And this particular metric is the heaviest 2-day total in 5 years. That frequency has changed over time. Well, I built the data set again, not from 1950 or not from 1920 or so on, but back to the 1860s. And what we see here in the Pacific, which is the upper one, is for the last 100 years, it's been about flat. There were some extreme heavy events back in the 1880s, 1860s. The biggest flood California ever had was 1861 to 1862. And so those events are folded in those first couple of bars. But overall, the trend is not significantly different from zero. When you start at after those first few. Then, for the southeast, we also have a trend that is not significantly different from zero, but if you start your line in 1958, you do get an upward trend, and you can, if you do the statistics right, say it's statistically significant. So that just tells you the occurrence of these heavy events every 5 years. When were they occurring? And that is what you see here. Nothing to get alarmed about that I can tell. So, was there a change in frequency of these things? Well, the CSSR report, which is the federal government, says, okay, if you have a 2 in 10-year event, that's now becoming a 3 in 10-year event. Well, that's not that big of a change. But using a longer time series, what I found is that a 3 in 15-year event is now becoming a 4 in 15-year event, which is not significant at all because of that up and down. The variations are just terrific there. But how about that heaviest day? Has it really changed in magnitude? That's the frequency. What about the magnitude? Well, when you're talking about, these are 10 stations in the southeast, when you're talking about how much rain falls on the heaviest day in a year, it goes up, and it could be 10 inches one year, 5 inches the next year, 12 inches the next. And over 150 years, I hope you can see that little red bar where it says the amount of increase in 150 years is that. Now compare that to the variation you see of the actual quantity, and you can say, what are we alarmed about with that type of increase when year to year the changes are so much greater in the heaviest rain per year? Now, and it's becoming, when you couldn't get people excited about that gradual rise in global temperature, you start saying, well, you've got to get excited about extreme events because these are terrible and we got great video of them and there's just more and more all the time. Of course, that is directly correlated with the number of cell phones we have with video capability today. Tornadoes, droughts, floods, whatever. It's your fault too, by the way. Well, all science is numbers, and so we can look and we can see, okay, let's look at all the stations, how many 100-degree temperature days occurred in the United States in the last 123 years. And this is the chart, looks a little familiar. But what you see here is that nothing is changing in the hottest days per year. The number of days above 100 or 105 is just going along pretty steady for the last 50 years, and not nearly as many as there were back in the 50s, 40s, 30s, and 20s. Global drought. With satellites today, we can measure global drought, and you see here there is no trend in the amount of area in the globe that is covered in different levels of drought. It's amazing what numbers can do when you bring them to the table on someone whose hair is on fire because they're so worried about global warming or something. What about wildfires? We've seen a lot of the car fire out in Northern California, for example, terrible images and pictures and so on. But let's look at the numbers. Here's 400 years of wildfires in North America. And you can see that in the first 300 years there or so, Mother Nature and Native Americans loved fire. And so there were just all kinds of numbers, huge amounts of fires occurring. And yet when the Western civilization came in and moved, especially into the Western United States and Canada, we didn't like fires. So we started putting them out. And so now you see that the number of fires has gone way down as a result of management policies. In fact, globally, this is decade by decade. The orange bars tells you how much in the globe burned in that decade. And you can see that there has been a steady decline. Wildfires are a function of the way we manage them, not really a function of this climate change notion that people want you to think about. And I can sit there on a Senate panel or something and tell a senator wildfires are going down, and it will go right over their heads in terms of information that they should be processing, and they will say in the next sentence, but wildfires are getting worse. Show me your numbers, and they don't have any. What about floods? That's the blue line here in the United States, month by month. It goes up and down. Some years are really wet, some years are not. Same with droughts, the red part, but there is no trend in either one of those statistics. Hurricanes, well, we have a slight downward trend actually for the global hurricanes. What happens in the Atlantic, remember, is a small part of what happens in the world, and so you need to take the whole world and see what hurricanes are doing there. And the energy that the hurricanes have, we have not seen the type of energy since about 1994 or so that occurred that year, but there is no trend. Lots of ups and downs, but no trend. How about tornadoes? Well, if you squeeze your eyes and kind of look there, it's actually a downward trend in tornadoes. The year with the least number of major tornadoes was last year. And in fact, in 2018, Oklahoma recorded their longest tornado drought ever. And that ended on May 1st when a tornado did occur there. Snowfall? What about snowfall in the northern hemisphere? This is the area extent of snowfall, and it goes up and down year to year, but there is actually no trend there at all. In fact, the heaviest year, the largest extent of snow cover was recorded just 5 years ago in 2012, 2013. So snow is still falling, as it always has. And finally, on this extreme thing, if you just look at, bundle this whole story together and say, well, how many damages have occurred? How much are the damages? You see there's actually a downward trend in the amount of damages from all these kinds of extreme weather that have occurred. So I hope you get the point here that extreme weather has not been changing, especially the kind of weather we care about. In other words, you are not at fault when Hurricane Florence, a Category 1 hurricane, strikes the coast of North Carolina. Here's another point. You should believe global climate models because they predict rapid changes. So we're going to test some climate models here. I think David might have some more information on this later. I just have a small part here. And we're going to talk about the temperature of the atmosphere, and that's where the greenhouse effect is really supposed to be apparent, as I'll show you in a moment. And we're going to use balloons and satellite data to check on this. And so to check on a climate model, see if it's really right or not, there's 4 tests that Ross McKittrick wrote out, and we published a paper just about a month ago in an AGU journal. 1, it should have the test of measurability, that we should have independent data sets available, multiple ones, to check against the models. Specificity, the results seen in all model runs over a specific period so we can specify exactly what we're looking at. Independence, make sure the parameter was not used in model development. When you see modelers compare their surface temperature with actual temperature, the actual temperature surface temperature was used in the model development, so that's not a test. So you need to do a temperature of something that was not used to develop the model. And finally, uniqueness, and this is something that emerges as the strongest pattern of model simulations, across all model simulations, and that is there when the effect is introduced and not there when the effect is out. So if you put greenhouse gases in your model, you see this effect. If you take the greenhouse gases out, you do not see the effect. So that's the uniqueness aspect. Okay, so those are the 4 characteristics, and we're going to look at this. Now, this is a cross-section of the atmosphere. The South Pole is on the left, the North Pole is on the right, up is up, so that's a stratosphere way in the top. The surface is at the bottom, so latitude is across the bottom. So think of it as a cross-section from the South Pole to the North Pole, left to right. So in the tropics, you can see, and this is a trend, temperature trend at each one of those layers, levels, and latitude. So you see that in the tropics, there's a big signal there. And that shows up in all the climate models. That red color down in the bottom right-hand corner, that doesn't show up in all the climate models. But this one in the tropics does. And so the satellite takes a temperature about from the surface to about 15 kilometers, that deep layer. Then we can use balloons to get just that part that's the hottest there in the tropics, and that's about the 300 to 200 hectopascal layer, about 10 kilometers above the surface. So that's our test metric. It's there in all the climate models. You take greenhouse gases, extra greenhouse gases out of the models, it's not there. So this is a test metric that is independent from the surface temperature data, more or less. So in this spaghetti chart, the red line is the average of all the climate models. The other lines there with the symbols on the lines are 3 very different types of data sets, but independent from the models. And they show that if you draw any kind of statistical test on these, we find that the models are significantly different than the actual data, or we would say in science, your hypothesis, which is your model, we have falsified your hypothesis. We have falsified your model. You need to go back and fix something. Now, in science, the way I was taught, that when your hypothesis failed, you would go back and change your hypothesis, or you would say, it's just wrong to begin with. Rather modify your hypothesis or say it was just wrong. In climate science, in climate models, when your model is shown to be falsified, you just scream louder that it's good. that's the way the reaction is among the climate modelers that we've dealt with. And they will try to find something wrong. Well, there's something wrong with the observation, but I have three completely different types of data sets, they'll find ways to try to explain this very wrong result. Now, for that balloon, that little strip up there in the tropics, the key metric there, you see that for the NASA models, and all the models are just like this NASA model, generally, but they get the same kind of result for the average, is that their trend is about 3 times more than what has actually occurred. And the observations have their trend partly because the last couple of years we had a big El Nino and that bumped the temperature up there at the end, but it will come down here in the next couple of years. But in my world, at least the way I'm thinking, if you're off by a factor of 3 with your model output, I would check something with the model rather than say, oh, but the model's still right, maybe it's the world that's wrong, something like that. The models just are too sensitive to CO2, and they are the ones that have been driving policy. So on the left, it starts at 0 on the bottom and goes up to 6 or so. And what that is on the left bar is the model, the theoretical range of what the sensitivity is of the temperature to doubled CO2. If we get up to double CO2, that's what the temperature would end up at. But those dots are actual empirical values. And we actually went out to real global data with energy fluxes and temperature changes and so on, and calculated what the sensitivity to doubled CO2 might be. And we came out with these much lower numbers. Mine's the next to the last one on the bottom right. And so it's, a good number to say is the models are just twice too sensitive. And so they get these dramatic results with their warming up the planet. 5, this is the last one. CO2 regulations will save the planet. So I presented this to a Senate committee a few years ago. The red line is what climate models say the global temperature will do. The green line is what will happen if the United States ceased to exist in 2012. In other words, no people, no cars, no factory, nothing. No oil drilling, nothing. You can see that that's a very small effect, and that's if you completely take the United States off the face of the earth. So we are not driving the bus on CO2 emissions anymore. That's from other countries, and for good reason. They just don't emit CO2 because they want to emit CO2. They emit CO2 because it brings them very important things in life. In fact, the green here is the amount, the green and black together, the amount of CO2 emissions since 1990. It has grown and grown and grown. As I say in the blue there, the drive to secure a longer and better life trumps environmental virtue. And when you look at these regulations, and I've done many for courts and other things, the regulations do absolutely nothing to change whatever the climate is going to do. And so that's just an environmental virtue. It's called virtue signaling, that you are doing something good, even though it has no effect and it costs people more. In the green there, I say 25 years of being scolded about CO2 emissions has not changed the fact carbon is a terrific source of energy today, and the world is using more and more of it. That's not an opinion, that's not right or wrong, that's just a fact. Look at the carbon emissions and you will see them rising because it brings people longer and better lives. And the average person, I think even in this room, would say, I would like a longer and better life. So what I've learned in my career about most claims regarding human impacts on climate is that thorough testing of the claims indicates changes are consistent with natural variations. Claims that model output is verified in observations are based on very specific cherry-picked parameters, while major and fundamental variables, as I showed, the tropical stuff, fail to be replicated, therefore the models fail. Human communities will find the most affordable way to have a better life. And finally, demonstrating that particular claims, hypotheses of climate alarmists are false ensures isolation, denigration, and criticism from the climate establishment. 36 hours after the March for Science, which had a big old emphasis on climate change, my office building was shot at. 7 rounds of a Belgian FN 5.7 high velocity rounds were found, and that's my office suite there. Because some people just think of environmental issues as if you have a different view, you are an enemy to be destroyed rather than an opponent to be engaged in rational conversation. We bring to this whole issue real, hardcore, published data to test the claims of these some fantastic claims about climate change, and we find those claims wanting. We find them failing simple hypothesis tests. So I'm through early, so thank you very much for your time.
John, you didn't really do the hotspot thing.
That was the hotspot in the tropics.
I know. You didn't talk about the fact that that hotspot issue was really a deadly problem for the people who were claiming their models worked. Could you explain it a little bit? I thought maybe that you might have not mentioned it in a way that would make an impression on people.
Well, I was talking about what he's talking about is that hot spot that all the climate models had right there in the tropics that we don't really see in the actual observations. And I think all I could say about that is when you point something like this out, you really create a storm. And there have been efforts to say our data sets are bad, but I put data sets together from all over the world. They're not all my data sets that verify the point we are making, that these models have way too much sensitivity to carbon dioxide. I think what it comes out to is this. When the real world heats up a little, it sends out that heat to space pretty effectively. In the climate models, when they heat up the atmosphere, there's a trapping mechanism that's not real, that keeps that heat in, and so over time, that's why their temperatures are rising so much. They don't have the proper mechanisms to allow heat to be released from to space. We measure that poor replication of the world, and yet it's hard to get that across to a climate establishment that literally has billions of dollars behind it moving in this direction.
Dr. Cristy, thank you for your talk. Steve Edcock, Resource Evaluations. A couple quick questions. One is relative to the language cycles and the whole sunspot issues that we're looking at now as being more related to some of the global climate things. We should be moving away from the sun, so overall cooling should be applied at this point. I'm just curious about your take on the traditional Milankovitch kind of approach and solar input. And the other is the geochemistry of CO2 as a greenhouse gas as opposed to worrying about methane and water vapor and things that are actually more greenhouse gas. I'm still yet to see a solid piece of evidence that tells me carbon dioxide would react the way they say it does.
Okay, relative to the solar angle, I think on the shorter time scale, 11-year, 22-year cycle, and so on, we still don't know all the ways in which the Earth is affected by that. It's hard to find a signal in the troposphere and at the surface. We can see it in the stratosphere and the mesosphere pretty well. So there's got to be some linkage there, but the theories out there that, the one that has some legs on it is the change in cloud cover, that if there are more cosmic rays coming in, they energize the aerosols and therefore more clouds are formed, and that reflects sunlight, making it cooler. And that evidently, has some legs, as I said. But the Milankovitch cycles, I think they're kind of outside this realm, but there is evidence that they certainly line up, especially the last 750,000 years, as a change in the amount of energy that hits the 65 degrees north that would melt the ice caps at the right time. The CO2 question, methane has a much less residence time in the atmosphere, so it reacts and so it goes away. I think 7 years is about it. CO2, I think what you're asking is, and I think I agree with you, is we really don't know that carbon cycle well enough to know, is it going to stay in the atmosphere 200 years? You know, a lot of things happen. Plants grow, you know, limestone's created in the oceans and so on. It might have a faster cycle time than what is thought of at this point.
Well, thank you so much, John.